Hey guys, welcome back. So today I'm going to talk about the transition step in cellular respiration and the Krebs cycle. So here's the story. So basically, you're finished with glycolysis and you form that pyruvate. So from that pyruvate, let's think about it as a pirate and the mitochondria as his pirate ship. So he enters his pirate ship using a porin, and then when he's in the intermembrane space, he has to go through a symporter. What that basically means is he has to enter using another shipmate. So he and a shipmate have to go together. So the pyruvate, a pirate, enters with another shipmate. They have to go through together to get to the matrix. Now once the pirate is in the matrix, the transition step happens to form acetyl-CoA. What that basically means is he goes through the pyruvate dehydrogenase complex. So once he goes through that complex, he releases off some gas, CO2, and he also releases NADH. Something else that also happens is CoA comes in to help out. So this is represented by a white van. You'll see what this means later on. So let's take a deeper look in what the transition step is and what actually the pyruvate dehydrogenation complex is. So this complex is three sets of enzymes. So the first one is pyruvate dehydrogenase itself. So pyruvate, when it enters the complex, so we're thinking of a pirate. So pirate comes in, he sees a TP, he wants to rest. So he enters the TP and he lets off some gas, CO2. So now once he's taken a seat in the TP, he becomes acetyl. So now we don't have a pirate anymore. Just think about this pirate always taking a seat. So now he's always going to be the acetyl. So he's bound to TP, which is represented by TPP, which is a bound cofactor here. So once he's all comfortable, but then E2 comes in, acetyltransferase. So what acetyltransferase mediates basically is the bound cofactor lipoamide coming, and it basically steals that acetyl group from the TP. So now that group is stolen, we have this molecule right here, this lipoamide with a sulfhydryl group here, a sulfur, and an acetyl right here. But then what happens is this CoA, which I represented by a white van earlier, let's just do the same thing. So a white van comes in and kidnaps the acetyl, the pirate sitting down, from the lipoamide. So now this white van kidnaps acetyl to make it into acetyl-CoA, the sitting down in that white van. So acetyl-CoA is then transported into the Krebs cycle, okay? But it does not end there. So now we have this lipoamide with no acetyl. So now you just have two sulfhydryl groups. So now what happens is, well, what this enzyme is lipoamide dehydrogenase. Once you hear the word dehydrogenase, bells should start going off in your head. Think NADH or think reduction. Or not only reduction, oxidation can happen as well, but think NADH, FADH, stuff like that. So the bound cofactor used here is FAD. So FAD comes in, takes this hydrogen and the electrons associated with it, and turns it into FADH2. This is bound. And now a mobile cofactor, which is NAD+, comes in and basically steals FADH, the electrons of FADH, to turn it into NADH. And this is used in the oxidative phosphorylation to make ATP. So basically the takeaways are the stars, the products formed. So acetyl-CoA is transported out, and then NADH is also transported out, okay? So basically what to know about how you can remember the mobile cofactors is they basically come in and steal another group, okay? Whether it be the acetyl or the electrons of the FADH2. So the overall reaction here is pyruvate plus coenzyme A plus NAD plus is equal to acetyl-CoA plus carbon dioxide plus NADH, okay? So now the molecule we want to be focusing on is acetyl-CoA and how we can make as much ATP as we can from that molecule, and that is going to be in the Krebs cycle. So let's move on to that. So let's talk about the Krebs cycle. So remember that white van with the acetyl-CoA? So it pulls up to the Krebs cycle where it meets oxoalloacetate. So think about it, the van meets an ox, right? Okay, so the van meets an ox, and the ox is carrying 4 barrels. So think about that as a 4-carbon molecule. Acetyl-CoA is a 2-carbon molecule. So the white van which kidnapped that acetyl group, drops off the acetyl onto the oxaloacetate, and it forms citrate, which is a 6-carbon molecule. So that, to wake up the acetyl-CoA, which was asleep because it was kidnapped, you splash it on with some water. So that wakes up the acetyl-CoA, which is now a citrate. And it's made using citrate synthetase. Easy to remember because synthase. Okay, so now that you have citrate, a 6-carbon molecule, using aconitase, an enzyme, it's turned into cis-aconitase. Now, this is more of an intermediate because the main intermediate is diisocitrate, but to know this easier, you can get rid of H2O to make cis-aconitase, and to remember that, you can use the orange juice example of citrate, meaning, let's say you have citrate, and basically, let's just pretend you have an orange, and you squeeze out the juice of an orange, which also has water in it, and you give it to your sister. So that orange comes out, the water comes out of the orange, and you give it to your sister, cis-aconitase. Now your sister is feeling thirsty, so she drinks the orange juice, which also has water, and it comes out to diisocitrate, because now the orange peel is now isolated. So diisocitrate. Now, what happens next is important because you form NADH. You also have CO2 as a metabolite coming out. So this CO2 coming out is called decarboxylation, and this is catalyzed by the enzyme isocitrate dehydrogenase. Remember, dehydrogenase, you're gonna have something to do with NAD plus and NADH. So here you're forming NADH. To make alpha-ketoglutarate, this is also called 2-ketoglutarate sometimes. So now, basically the same reaction is gonna happen. So now you go from alpha-ketoglutarate to succinyl-CoA using alpha-ketoglutarate dehydrogenase. Again, this is a decarboxylation reaction. So the CO2 comes out and you form NADH. Remember, we are losing carbons. So we started off with 6 carbons. This is 6 carbons, 5 carbons. Now this is 4 carbons. So we lost 2 carbons. So now we have succinyl-CoA. So an easy way to remember from going from isocitrate to alpha-ketoglutarate is basically you switched from an orange diet to a keto diet. And then you go from a keto diet, the keto diet sucks, right? So succinyl-CoA.
Go.
Okay, and so moving on to succinate. So you go from succinyl-CoA to succinate, and to remember succinate, well, it sucks. The keto diet sucked, right? So you ate a lot, succinate. And now, since you ate a lot, you have a tendency to smoke. So you smoke. If you don't know, fumar means to smoke in Spanish. So fumar, which is bad, mala. And then you do all of this next to an ox, and then this ox goes back to the white van, which restarts the cycle. So just to recap, remember succinate, fumarate, malate, and then oxaloacetate. And to recap on the enzymes. So we went from alpha-ketoglutarate dehydrogenase, turned it into succinyl-CoA. And now from succinyl-CoA, we're going into succinate. So we use this enzyme called succinyl-CoA synthetase. So that produces GTP as a byproduct, and that is equivalent to 1 ATP. And succinate to fumarate actually is a membrane-bound process. So what that means is succinate dehydrogenase is actually complex 2 in the electron transport chain. So what happens is you have Q, ubiquinone, and it's basically turned into hydroubiquinone. So what happens is here, it gets a donation of electrons inside the complex itself, and basically there is an FAD and FADH2 complex process inside the complex itself, but the ultimate result of this is the QH2. So after that, the fumarate then goes to malate via hydration. So you can almost think of it to remember the H2O coming in. You're smoking and you put it out because it's bad. And from malate to oxaloacetate, it's actually, I'm gonna put this in, so this is malate dehydrogenase. So it goes from NAD plus to NADH, okay? And this, we actually didn't put this the other, so sorry about that, but this is fumarase. Okay, that's pretty easy to remember, fumarate into malate fumarase. So dehydrogenase, so here, this is the only dehydrogenase reaction within the Krebs cycle where there's no decarboxylation happening. So here and here there was a decarboxylation, here there's no carbon being lost, it's just the NADH being formed. So, and then it goes back to start. So this cycle happens twice with one molecule of glucose, forming 24 ATP. How is it 24 ATP? Let's take a closer look. So we form 3 NADH from one turn. That's equal to 9 ATP, as 1 NADH is equal to 3 ATP. 3 times 3 is 9. We have 1 GTP, which is equal to 1 ATP, and 1 QH2, which is equivalent to 2 ATP. Okay, and adding that together, that's 12 ATP. Okay, and basically, this NADH is going to be made into the ATP using oxidative phosphorylation. And just a quick recap, a quick summary of oxidative phosphorylation. You basically go from NADH to Q to cytochrome C to oxygen. So that's the flow of electrons in the oxidative phosphorylation. Okay, so that's the flow of electrons in oxidative phosphorylation. So all of this has a purpose. The ATP is being formed in oxidative phosphorylation. So that was the story of Krebs cycle. It might have been confusing here and there. Just rewind and